Hello sir, hello guys. So we're from group 8. We're going to talk about magnetic forces and magnetic fields. Okay, so magnetism. What is magnetism? Magnetism is simply the force that can attract or repel objects that have a magnetic material inside, like iron and such. Okay, so law of magnetism. Law of magnetism. The most basic law of magnetism is that like poles repel each other while unlike poles attract each other, and the pole ends of a magnet are north and south poles.
There are 5 types of magnetism.
Diamagnetism. It is displayed by all materials. The tendency to be repelled by a magnetic field. Other types of magnetism can be stronger than diamagnetism, so only observed in materials that contain no unpaired electrons. Weakly magnetized in the opposite direction of the applied field. Examples of diamagnetic materials include gold, quartz, water, copper, and air. Another is paramagnetism. There are unpaired electrons. The unpaired electrons are free to align their magnetic moments. The magnetic moments align and are magnetized in the direction of the applied field, reinforcing it. Examples of paramagnetic materials include magnesium, molybdenum, lithium, and tantalum.
Third one is the ferromagnetism. Ferromagnetism materials can form permanent magnets and are attracted to magnets. A ferromagnet has unpaired electrons, plus the magnetic moments of the electron tend to remain aligned even when removed from a magnetic field. Examples of ferromagnetic materials include iron, cobalt, nickel, alloys of these metals, some rare earth alloys, and some manganese alloys. Fourth one is the antiferromagnetism. In contrast to ferromagnets, the intrinsic magnetic moments of valence electron in an antiferromagnet point in opposite direction is like anti-parallel. The result is no net magnetic moment or magnetic field. Antiferromagnetism is seen in transition metal compounds such as hematite, iron, manganese, and nickel oxide. Last one is the ferrimagnetism. Like ferromagnets, ferrimagnets retain magnetization when removed from a magnetic field, but neighboring pairs of electron spins point in opposite directions. The lattice arrangement of the material makes the magnetic moment pointing in one direction stronger than the pointing in the other direction. Ferrimagnetism occurs in magnetite and other ferrites. Like ferromagnets, ferrimagnets are attracted to magnets. Thank you. Other types of magnetism are superparamagnetism, metamagnetism, and spin glass.
Properties of magnet. There are 3 properties of magnet. First is the attractive property. Magnet attracts ferromagnetic materials like iron, cobalt, and nickel. Second is the repulsive properties. Like magnetic poles repels each other, and unlike magnetic poles attract each other. And third, directive property. A freely suspended magnet always points in a north and south direction. Magnetic field. So what is magnetic field? A magnetic field is a region around a magnetic material or a moving electric charge within which the force of magnetism acts. Magnetic fields surround and are created by moving electric charges such as those used in electromagnets.
Hello.
Magnetic force. What is magnetic force? Magnetic force is the attraction or repulsion that arises between electrically charged particles because of their motion. Simply put, it is caused by the motion of charges. Two objects containing charge with the same direction of motion have a magnetic attraction force between them. Similarly, objects with charge moving in opposite directions have a repulsive force between them. The magnetic force between two charges may be described as the effect exerted upon either charge by a magnetic field created by the other. The formula for finding the magnetic force is described by the magnetic part of the Lorentz force law and describes the force due to the electric force. The electric force works between stationary charge. So the formula is F, or magnetic force, is equal to the amount of charge times velocity and times the magnitude of the magnetic field. A particle with a charge of 2 microcoulombs is moving at 3.106 meters per second, perpendicularly, through a magnetic field with a strength of 0.05 Tesla. What is the magnitude of the force on the particle? The given for this problem is Q, or amount of charge, is equal to 2 microcoulombs, or we can convert that to 2 times 10 to the power of negative 6 coulombs. Our second given is the velocity is equal to 3 times 10 raised to the power of 6 meters per second. And last, our magnitude of the magnetic field, or B, is equal to 0.05 Tesla. Our required value is F, or our magnetic force. The solution to this problem is we will use the formula F equals Q times V times B. So we plug in the values. So the charge is 2 times 10 raised to the power of negative 6 coulombs times 3 times 10 to the raised to the power of 6 meters per second times the magnitude of the magnetic field, 0.05 Tesla. So we multiply all of these values to get the force, which is 0.3 newtons. The previous formula can be written in terms of the angle theta, which is less than 180 degrees between the velocity vector and the magnetic field vector. So the formula is F, or magnetic force, is equal to the amount of charge times velocity times the magnitude of the magnetic field and times the sine of theta, or the angle. The sample problem for this is a particle of charge positive 7.5 microcoulombs and a speed of 32.5 meters per second enters a uniform magnetic field at an angle of 30 degrees whose magnitude is 0.5 Tesla. What is the magnitude of the force on the particle? To solve this problem, we also have to identify the required given and solution. So for this problem, the given is amount of charge, 7.5 microcoulombs. We convert that to 7.5 times 10 raised to the negative 6 coulombs. And we have the velocity, 32.5 meters per second. The magnitude of the magnetic field is 0.5 Tesla, and our angle is 30 degrees. Our required is force, or the magnetic force still. Our solution for this problem is to use the formula F equals QVB and the sine of theta, or the angle. We plug in the values of these variables, which is 7.5 times 10 raised to negative 6 coulombs times 32.5 meters per second times 0.5 Tesla and sine 30 degrees. After multiplying all these values, we get the force, which is 6.1 times 10 raised to the power of negative 5 newtons. How to determine the direction of the force? The direction of the force can be found using the right-hand slap rule. It describes the direction of the force as the direction of a slap of an open hand. The fingers point in the direction of the magnetic field. The thumb, on the other hand, points in the direction that positive charge is moving. If the moving charge is negative, for example, electrons, then you need to reverse the direction of your thumb, because the force will be in the opposite direction. Alternatively, you can use your left hand for moving negative charges.
The formula for force on a wire is magnetic force equals magnetic field times the current in a magnetic field times the length of the wire times sine theta.
Hello guys, so this is an example or a problem on force on a wire. So let me read it for you. So the figure shows a wire running through the north and south poles of a horseshoe magnet. A battery is connected to the wire which causes a current of 5 amperes to flow through the wire in the direction shown. If the magnetic field between the poles is known to be 0.2, what is the magnitude and direction of the force on the 10 mm section of the wire between the poles? So we are trying to find the force. So based from that problem, we have gathered this. Magnetic field between poles, or B, is equal to 0.2. I, which stands for current, is equal to 5 amperes. And length is equal to 10 millimeters, which we will convert to meters. It is equal to 0.01 meters. So given by that value, how do we solve for the force? We will use this formula, which is equal to F is equal to BIL sine theta, which means that F stands for force, B stands for magnetic field between poles, I which stands for current, and L stands for length. So how do we solve for sine theta? In this exercise, the magnetic field lines which run from north to south form a right angle 90 degrees with the direction of the current flowing in the wire. So sine theta, as we all know, is equal to 1 since the angle is a right angle or equal to 90 degrees. And this term can be removed already since it's the value of sine theta is 1. We can already remove it from the formula. The force can be evaluated as this, but for the sake of example, I'm gonna put 1. Force is equal to 0.2 multiplied to 5 amperes multiplied to 0.01 meters times 1, which is equal to, if you calculate it, it will be equal to 0.01 newtons. So the force on a wire is equal to 0.01 newtons. Thank you.
Motion of a charged particle in a magnetic field. Magnetic forces can cause charged particles to move in a circular motion or spiral path. Particle accelerators keep protons following circular paths with magnetic force. The magnetic force is perpendicular to velocity, and so velocity changes in direction, but not magnitude. Uniform circular motion results. So the formula for the motion of a charged particle in a magnetic field is F, or magnetic force, is equal to the mass times squared velocity of the charged particle divided by the radius. A sample problem is as follows. A proton traveling at 1 × 10 to the power of 7 meters per second in a horizontal plane passes through an opening into a mass spectrometer with a uniform 3 Tesla magnetic field directed upward. The particle then moves in a circular path through 180 degrees and crashes into the wall of the spectrometer adjacent to the entrance opening. How far down from the entrance is the proton when it crashes into the wall? The proton's mass is 1.67 times 10 to the power of 27 kilograms, and its electric charge is 1 × 6 times 10 to the power of -19 coulombs. So for the sample problem, you will also be finding the given, required, and solution. So for the given, we have the mass, which is 1.67 times 10 to the power of -27 kilograms. For the velocity, we have 1.0 times 10 raised to 7 meters per second. And the charge, which is 1.6 times 10 raised to the power of negative 19 coulombs. Lastly, we have the magnitude of the magnetic field, which is 3 Tesla. For our required is the R, radius, and the distance. This is the diagram for the sample problem. In our solution, a charged particle moving through a magnetic field feels a Lorentz force equal to this formula. F equals charge times velocity times magnitude of the magnetic field. Q is the charge, V is the speed, and B is the magnetic field strength. This force is always directed perpendicular to the particle's direction of travel at the moment, and thus acts as a centripetal force. This force is also given by the equation F equals mv squared over r. So we can set these two equations equal to one another, allowing us to solve for the radius of the arc. So we join these formulas to get this formula. QVB is equal to mv squared over r. To get this formula, which is r equals mv over qb, simplified formula. So once the particle travels through the semicircle, it is laterally one diameter in distance from where it started, i.e. twice the radius of the circle. So r is equal to 1.67 times 10 raised to the power of negative 27 kilograms times 1.0 times 10 raised to the power of 7 meters per second, all over 1.6 times 10 raised to the power of negative 19 coulombs times 3 Tesla. So we compute this to get the radius, which is 34.8 millimeters. Twice this value is the lateral offset of its crash point from the entrance. So 2 times through the radius, 34.8 millimeters, we get 69.6 millimeters.
Thank you.